The constraints-led approach focuses on enabling individuals to acquire coordination and movement control over time to help build a better understanding of issues. This theoretical framework, which is a non-linear pedagogy, determines how individuals acquire and organize movement patterns as a response to constraints. The interaction of constraints, task, environmental, organismic, influences the individual to self-organize and self-discover movement patterns in order to generate functional movement solutions. The perceptual motor landscape is an open system which explores the ability for the learner, a complex system, to adapt to a dynamic and changing environment. Learners assemble functional movement coordination solutions through self-organization in order for new attractor states to emerge. Learners transition through different learning phases, which are temporary states of coordination, and resist new constraints that have the ability to break attractor states in unpredictable contexts. Hence, learners must develop a variety of movement attractor states in order to emerge and adapt in response to a multitude of constraints within a topological context. In order for optimal movement patterns to occur, an increase in practice time and variability will lead to improved performance ability and ultimately allow for the transfer of motor skill learning. Therefore, I'll be completing a 20-hour program with my motor skill being basketball shooting, varying distance in order to achieve multiple attractor states. In functional equivalence, which is the ability to produce action in a variety of different ways to develop attractor state, distance will be a control parameter, which affects the emergence of a coordination pattern, resulting in different coordination patterns still achieving the same outcome. Basketball is a highly dynamic sport in which players must perform shots from several distances from the basket. Longer shots demand greater movement accuracy because the horizontal visual target decreases as shooting distance increases. Therefore, according to Okazik and Rodaki's study in 2012, when the shooting distance increases, the player must reduce the ball release angle trajectory and the ball follows a flatter flight path, which is a task constraint to consider. Proprioception is the awareness of one's own body and spatial position independent of visual input. Proprioceptive feedback plays an essential role in both learning new tasks and adjusting existing skills in response to movement errors. Learners are focused on knowledge of performance, where less feedback is provided in order to allow for self-discovery. However, according to Aiken's study in 2011, visual feedback on knowledge of performance has seen to facilitate learning in a basketball set shot motor skill during transfer of learning through self-efficacy. Alternative theories to consider include Schmidt's schema theory, which emphasizes that a generalized motor program governs the movements which belong to the same class because they share invariant features. This is important to consider, as I have had previous experience when I was younger playing basketball under manipulated task constraints. Additionally, the contextual interference theory emphasizes the roles of contextual factors that are internal and external to both the task and learner. The practice context and the processing engaged by the learner were seen as potential sources of interference that could enhance or reduce learning. Schmidt's schema theory and the contextual interference theory suggest that higher practice variability leads to improved learning and retention of skills in varying contexts. Hence, in correlation with the power law of practice, as well as previously mentioned theories, it is hypothesized that a monotonic relationship will occur, in which, as practice time increases, performance ability will subsequently increase. For my training program, I divided each session in 2-hour blocks over 5 weeks in order for effective learning to occur, therefore resulting in 10 separate sessions with the aim to effectively manipulate constraints. Each session I completed 100 shots, where accuracy of shots scored in the basketball hoop was assessed in order to determine overall improvements throughout the program. Within hours 1 to 2, I focused on familiarizing myself with the ball by bouncing it on the court and throwing it towards the hoop. Hours 3 to 4 was focused on practicing set shots, with the concept of shooting hoops being classified as a task constraints. Hours 5 to 8 were focused on achieving a stable state in set shots and refining functional movement patterns. Hours 9 to 12 were focused on varying distance, which is a significant task constraint to consider in order to achieve multiple attractor states through functional equivalence. Hours 13 to 20 were focused on refining functional movement patterns, which improves the ability to adapt to a dynamic environment and task constraints. Overall, the training program provided a constructive guideline and direction to follow to improve motor skill learning in basketball set shots. The results proved an increase in basketball shooting accuracy by 58%. Hence, according to the figure, during session 1, 24 shots were accurately shot in the basketball hoop, respectively followed by 33 in session 2, 41 in session 3, 49 in session 4, 54 in session 5, 58 in session 6, 61 in session 7, 67 in session 8, 76 in session 9, 82 in session 10, ultimately providing a positive linear relationship between time practiced and number of shots taken. As a learner, I self-organize my degrees of freedom in response to constraints within the context. Within this program, the ball is considered a task constraint, where the weight and size are an important control variable. However, the most essential task constraint was aiming for shooting the basketball within the hoop, proving accuracy. Environmental constraints that were essential to consider consisted of the court surface, weather, and sunlight exposure, which when manipulated all contribute to affecting performance ability. Additionally, previous experience in basketball was essential to account for as an organismic constraint, as this would ultimately determine the extent of improvement. Another organismic constraint consisted of my shorter height and limb length, as I am not the typical demographic of a basketball player, hence a contributing factor in limiting my performance ability. Overall, these constraints interact with my internal dynamics and contribute to creating the ideal learning environment. In hours 1 to 2, I familiarized myself with the informational constraints of the open system environment, where sensory information propelled movement responses. The idea of visual perception perspective was important to consider as it involves interpreting the effect of observational learning. Motor behavior observation, also known as relative motion information, included factors such as spatiotemporal awareness, where the relationship between limbs and the environment was affected by determining distance from the hoop. Relative motion information is useful in early learners as it guides perceptual search through proprioceptive feedback. Hence, learners afford low elbow technique of basketball shooting, which is determined by individual intrinsic dynamics of height and strength, where perception information is determined through fixating the visual gaze on the target prior to the release of the ball to improve shooting performance, ultimately encouraging variability through repetition shooting, allowing for self-discovery and search techniques to afford functional movement solutions. In hours 3 to 4, the learning process allowed for self-discovery of the physical constraints of the perceptual motor landscape, where stabilization and destabilization occurred in response to error detection, ultimately allowing for the emergence of an attractor state and therefore the retention of information. Additionally, simplification techniques such as isolating the shooting technique were used to break down the skill and allow for adaptive training, in order to make it easier to form attractor states. Through this, the learner allowed for information movement coupling in order to effectively produce the movement. Additionally, during the session, knowledge of performance, such as missing the hoop, was beneficial for learning, as it provided proprioceptive feedback to afford functional movement solutions and self-discovery, leading to the emergence of an attractor state. In hours 5 to 8, it was essential to consider the environmental constraints, as they were manipulated through context variation. For example, change in location could impact attractor states. Court availability resulted in sharing a reduced space. Rain could prohibit playing outdoors, as well as darkness or overexposure of sunlight could affect vision and proprioceptive feedback. The change in variables led to improving self-discovery techniques and context adaptation ability. Furthermore, the manipulation of environmental constraints also promoted practice variation, which is important as a learner. Hence, the transfer of learning is prevalent by adapting to different environments, improving external information retention. Additionally, I manipulated a task constraint by pumping the ball up more, leading to more shot affordances as it is bouncier and easier to throw. Ultimately, an attractor state of set shots was achieved as my intrinsic dynamics matched the task dynamics, hence affording functional movement solutions. In hours 9 to 12, the scanning procedure was used, probing the entire perceptual motor landscape. This procedure allows for alteration of the order parameter, which is a change in behavior, resulting in adaptation and attunement to different movement patterns. During this session, the task constraint of distance variability was manipulated in order to progress the motor skill of basketball shots. Skill variation, which is expressed through functional equivalence, is important for the learner to be able to achieve multiple attractor states and therefore ultimately improving performance. The learning process allows for self-discovery in the perceptual motor landscape, where stabilization and destabilization occurs in response to error detection, ultimately allowing for the emergence of an attractor state and therefore information retention. A positive transfer of learning was determined as the perceptual motor landscape attractor state was functionally adapted to varied contexts and task constraints of distance variability. Hence, the concept of the nonlinear pedagogy was evident as practice variability represented fluctuations in movement coordination patterns through adapting under manipulated constraints in a dynamic and topological environment. In hours 13 to 20, an attractor state of varying shot distance was achieved as my intrinsic dynamics matched the task dynamics, resulting in functional movement solutions. Hence, the learner strives to achieve efficient and economical energy usage. In this stage, during late learning, visual observation of relative motion helps in perception of dynamic features for optimal scaling of movement patterns. For example, proprioceptive feedback is used at different distances to determine the affordance of technique in basketball shooting, ultimately allowing for the intrinsic dynamics to match with the task dynamics and requirements. During these sessions, optimal movement patterns were prevalent with multiple attractor states achieved. Thus, if I was to add an additional 20 hours to my learning program, it would be focused on shooting under time and opposition pressure in order to transfer learning into a realistic learning environment. Throughout the 20-hour program, there were a multitude of obstacles and boundaries to overcome in order to improve basketball shooting accuracy. The strengths consisted of reassessing after each session, every 2 hours, in order to determine stable states formed in subcomponents of the skill, as well as the consistent concept of shooting 100 shots per session. In addition, I maintained my organismic constraints throughout, allowing for reliable results. However, in regards to weaknesses, the 2-hour sessions were quite long, and I would get tired towards the end, which could have altered results. Additionally, the environmental constraints were consistently changing, such as weather, sunlight exposure, and court surface, also leading to potential unreliable results. Overall, basketball shooting is an extremely difficult motor skill to master over 20 hours, as distance is constantly changed through task manipulation in a typical basketball game. Furthermore, when practically applied, a basketball player requires multidimensional attention when under external pressure from opponents and time, which is severely limited when practicing and learning individually. Furthermore, in terms of practical application, the motor skill of taking a shot in basketball can be applied within a basketball game context, where shooting in the hoop will result in higher scoring, with the objective to win the game. In particular, free throws attribute to 1 point, shooting within the D will attribute to 2 points, and shooting outside of the D will attribute to 3 points, ultimately signifying the necessity of practicing shots from different distances and the importance of task constraint manipulation. Overall, a monotonic relationship was present throughout the 20-hour program, in which, as practice time increased, performance ability subsequently increased. Thus, it was effective in applying the constraints-led approach to the training program, allowing for significant improvements in motor skill learning of basketball shooting.